Hello, welcome to everyone. You all have a test this weekend. I should just point that out in case you have not received an email or were not told. Um, I will just outline briefly what the main topics are on that test for all of you. It is basically everything you did with us during September. So you will have done a lesson on cells at the very beginning. You will have done a lesson on atomic structure in chemistry. It was called atomic structure, ooh, and the periodic table. You will have done a lesson on energy in physics, and you did some rearranging equations in maths. Everything you have done more recently shouldn't be part of the test. By more recently, I mean the last couple of weeks. Um, um, ooh, can everybody hear me? Someone's saying that I'm muted, but I don't think I am. How will you help me with my chemistry thing? If you good, you can hear. I can't remember what that chemistry thing was, but I think it was because you had some questions on the chemistry homework. So if you do have questions out after you have checked those notes that I gave to you, then just let me know and I will get back to the chemistry homework as well. But for to start with, everybody in Key Stage 3, actually, year 7, 8, and 9, I think had the same homework because we this homework is so good, because of the number of equations and practice in it. I think we give it to everybody at the same time. So the first question so this will make life easier, and we might have a slightly shorter session as a result of that because everybody has the same one, which is this document. As a reminder, what you were supposed to do with this document is look at all of these equations that are given to you on the first couple of pages, and then you can use those to answer all of the part A's because it just means looking for the equation from that equation sheet. But then part C and B, C, and D require you to put those numbers into an equation and deal with it like that. Um, yes, so I just want to confirm again, the majority of those questions that you are asking me about on the chemistry, if you look through those notes, a lot of them were answered um, in the notes. But if there's anything beyond what I already answered, then you can feel free to ask me. Um, yeah, as I say, I'm not muted for others, so they seem to be able to hear me. So I think you need to check your speakers on your end. Well, I mean, I can't say anything because you can't hear me. So, um, yeah. Um, Right. I've been asked questions five, A, B, and C. So I'll start with that, and then I'll just talk around these equations a little bit more as we go. Um, and so, yeah, we'll do that. So, the question says a solar panel. Oh, there's no equation in this. That's interesting. A solar panel is able to output 120 kilojoules of electrical energy for every 200 kilojoules of light energy that it collects from the sun. Calculate the efficiency of the solar panel. Okay, let's pretend that you saw this question for the first time and you had no idea what was going on. Now, given that you have an equation sheet, okay, and the question refers to the word efficiency, you're probably looking for an equation that mentions the word efficiency, such as one of these two. And if you look at them, they're basically the same thing with a few minor differences in words. Um, and so I'll just pick one of them. Can't really read the question properly, so I don't know which one's relevant, but they are both basically the same thing. So we'll just take that down and talk about it. It was the correct one. Right. So there is an equation that says the following: that to calculate efficiency, you take the useful output energy. Now, output, it mentions 120 here. So I'm going to put that there. And you divide it by the total energy you've input. And it mentions for every 200 kilojoules of light energy that it collects from the sun, that is the energy that's gone in. A solar panel is something that takes light energy from the sun and turns it into electricity. And so in this question, what you had to do was 120 divided by 200, which is 0.6, I think, but you can use a calculator. I'm fairly sure that's 0.6. See what else anybody's saying. Oh, it works now. I got 60%, and that is fine. 60%, 0.6 are the same thing because a percentage can be written as a decimal. which can be written as a fraction. It's up to you. There are three versions of the same thing, which I think people sometimes forget. That percentage, fractions, decimals are really the same thing in different forms. Okay, and then an improved panel, so an even better solar panel, has a better efficiency. So we got 0.6, it's got a better efficiency. Calculate the electrical energy output that 80 kilojoules of light energy will generate. So what I'm going to do, just for simplicity, is simplify this formula to efficiency equals um, output energy divided by input energy. So just use O and I to avoid me writing lots. Um, they have told you that the efficiency is 0.75. So I'm going to write that there. The calculate the output. So we're going to calculate O that 80 of light energy will generate. So I'm going to put 80 there. At which point you would get a calculator out, which I don't seem to have here. Let me open up my calculator. And you would rearrange this equation. And that's what the challenge is in this, is whether your maths is good enough to do what happens next, which is to work out what this value here is, you would multiply 80 by 0.75. And you would get 60 as the answer, which is confusing because it was 60 before. Let me see what else anybody is saying. 6 and 7. Yes, I'll do 6 and 7 after that. Yeah, all the booklets are the same, just to be clear. So all of you guys in years 7, 8, 9 kind of thing have had the same homework booklet. So on this occasion, you don't need to say the booklet number. Um, Yep, so that part C then an even a newer one has an efficiency of 0.8. So using this formula again, efficiency is output divided by input. Um, Efficiency is 0.8. Calculate the amount of light energy required, that's what we're putting in, to produce 1200 electrical energy. So it's not easy, this question, because it doesn't phrase it as clearly as some of the other questions, but this is the useful output energy. And then we're trying to work out how much we're putting in, because you put light energy into a solar panel, you get electrical energy out. So I'm going to put 1200 there divided by I. Okay, so I need to work out what this value here is. So I won't go into too much detail, but to work out what I is, you do 1200 divided by 0.8. And you'll get 1500. So if we put 1500 joules of energy into this, we'll get 1200 electrical out, because some is always wasted, and that is life. Um, oh. um, 1 CED booklet 3. Yeah, right. I'll do so after this. Can you do 6 and 7? I'll do this in order of that I've been asked in. So 6 and 7. So this is number 6. I can see why these were problematic. So compared to some of the other questions, just a tiny bit harder. So this time, again, it mentioned the word efficiency and power. And this was what you get better at, which is if you read the question and look at the words in the question, then you start realizing which equation is relevant for the question. In this case, it mentions efficiency and power. So it is going to be this equation here. And this comes with practice, which is why you're doing this at the moment. Um, okay, so put that there for now, just to help me. Okay, a wind turbine has an efficiency of 0.45. So efficiency is 0.45. Calculate the power output, so the output, when the input is 25. And so to work out what that value there is, you will do 25 times 0.45, and you'll get the answer, which is 11.25. Now, there is one thing that somebody observant might ask me, which is why am I not converting the units? For example, why did I not change kilowatts to watts and stuff? And it's mainly because because of the way this question is asked, because we have both a number at the top and a number at the bottom, which is the same. It doesn't matter what units you use as long as they're both the same, basically, which is not the best explanation. Question 1, a few people have asked. Okay, let me get through this and then I'll get to them. Calculate. So once again, the equation is efficiency equals output divided by input. What does the question say? Calculate the input required for the same wind turbine, which has an efficiency of 0.45. To output, wait, hang on, input required to output of, not very good English. Calculate the power input required for the same wind turbine to output 35 kilowatts. So we're trying to, once again, work out the output if the input is 35. So this time you'll do that times that, which is 15.75. Done. Next question. Same equation. Efficiency is output divided by input. What does it say? An improved wind turbine can output 45 kilowatts, 45, if the input is 80. Calculate the efficiency. 45 divided by 80 is 0.5625. Is that better than it was before? Yes, it is. Okay. Right, good. Right. That's question 6 done. Right, that seems to be done. Let me go back to where I was. 6 and 7. Yeah, 7. Right. Again, look, this is really important. First part mentions write down the equation that links current, charge flow, and time. How are we going to do that? We will find the equation that has the words current, charge flow, and time in it. And there it is. Charge flow equals current times time. I'll write that down. Okay, from which point the rest of the question should hopefully be easy. A light bulb draws a current of 0.12. Current 0.12. Calculate the amount of charge that flows through the bulb in 2 minutes. Right, this is where you have to be very careful. In physics, whenever you see time, any sort of time mentioned, make sure that when you put it into an equation, you have converted it to seconds. Must do that. 2 minutes is 120 seconds by my calculations. So the charge flow is 0.12 times 120, not times 2, which will give you 14.4. And that would be the answer to the question. Next question. Again, we're using the same equation. Charge flow, I'm going to put C, equals, the symbol for current is I. So I'm going to just put that just to not have another C, basically, here. A bulb that draws a current of 0.12 can supply 21.6 of charge. This is the unit for charge. It's called coulombs. You don't need to know that for today. So I'm going to put the charge as 21.6, and we're timesing it by time. The question is how long the bulb will stay lit. In other words, what is the time? So what we're going to do now to work out what the time is divide 21.6 by 0.12. Because that's maths. 180 seconds is the answer to the question. And once again, charge flow equals current times time. A charge is 240, so let's put that there. Current is what we're working out. The time in this question is 30. So I put 30 there. Again, look how I'm setting it out, important. And your current will be, same thing again, you will do 240 divided by 30, which by my reckoning is 8. And so that is the answer. And that's all them done. 6 and 7 done, 6B done, 1 CD. Right, go all the way to number 1. Okay. So the formula, again, if you find the formula sheet, an equation that has force, work done, and distance in it, you should find something that says work done equals force times distance. You have asked me for C and D. Okay. So the phrasing of this question can make it seem confusing. So when it says, so just to be clear, work done equals force times distance, it says 14 joules of work are done. That means work done. Work done, just so you know, is a type of, it's just the same as energy. That's actually all it is, hence the same unit for energy. So 14 equals, the force is 15, and the question is calculate the distance. So the distance will be, if you divide the 15 across 14 divided by 15, which we will just write as 0.9. It's enough for that. And D, you asked for as well. Again, work done equals force times distance. Distance is 30. Motor does 230 joules of work. That is work done. Again, 230. Calculate the force, it says. So we will just divide 230 by 30 in this case, and it'll give us a weird answer of 7.7. I'll do. Okay. One is done. Someone just said the word eight. Is that question eight? Are you referring to question eight? Have I done that? Have I done that? No. I'll come back to that in a second and see what else is in here. 9, 12, and 11, please. 1C done. So the answers in this case, yes, we would normally you need units in your answer, but often what you will find in an exam, and not in this homework, you will find. So, for example, this question was current, right? Current is measured in a unit called amps. Now, what you will normally find in an exam in this kind of question, they will leave this space for where you put your answer, and they will put the units already there. So you just need to put the number. If the question said state the units in your answer, yes, you would need to make sure that wouldn't be there, and then you would need to state the units. For the purposes of this homework, because we are focusing more on you just using equations and rearranging them, you don't need to put the units in the answer for these questions, okay? But ordinarily, be aware that you do need to know the units for most of these things, that time is in seconds, current is in amps, and all of that stuff. Right, question 7C, I've already done. The answer is over here. 8, I will come to, but I just want to answer what everything's before 8 first. 1C, I've done. 9, 12, and 11, I'll do in order. Somebody has just asked me about 4D. Do that. 4D. Okay, I'll go straight to 4D. Oh, I have to do B as well, aren't I? Write down the equation that links power, energy transferred, and time taken. So, let's find that equation. Power, energy, and time taken. There. Power equals energy transferred divided by time. Okay. I'll have to do part B because I can't do that. Can't do D without it. A motor is used to drive a toy car. The motor transfers 200 joules of energy, so the energy is 200 in 20 seconds. Time is 20. Calculate the power. So 200 divided by 20 is 10. So the power we're going to have is 10 for that part B. Let's move straight to part D now. Calculate the amount of energy the motor can transfer in 1 minute. 1 minute is 60 seconds because we have to convert minutes to seconds. Energy is power divided by time. So we're going to calculate energy. Time in this question is 60. The power it tells you to use the answer from part B, which was there. So 10 divided by 60, which is 0.16 or something. Something like that should be enough. Okay. That dealt with that. And then 8. I don't do the whole thing here. Calculate the equation that links potential difference, current, and resistance. I should know this, shouldn't I? In the formula sheet, it should tell you something like, I know I should check this because I don't know what version it will be on it. There, potential difference equals current times resistance. For now, again, we're not worried about you understanding all of these words, but just realizing that if you have an equation, you should be able to use it. Potential difference equals current times resistance. I'm just going to leave that. Current is, again, usually the letter I. Right, I'll do all of it then. Current, so let's write this down. Potential difference equals current times resistance. The question says current 11.5, potential difference 230, resistance is what we're trying to work out, so we will divide this over 230 divided by 11.5. You did a lesson on rearranging equations not long ago, which is on your test at the weekend. So all of this stuff should be quite comfortable. 20 ends up being the answer to that question. If you care about the units for resistance are called ohms. But as I say, not important for this for now. C, again, I'm going to write the equation down to tell you how important it is. Okay, a lamp has a resistance of 80, so put 80 where the R is. 230, okay, it's a little bit awkward this. So potential difference is measured in a unit called volts, because it's actually the same as something called voltage. So what they're telling you without explicitly saying it is that this is the potential difference in this question, which makes that a little bit harder, I accept. And so if I want to work out what the current is, I will divide 230 by 80 and get 2.875. And lastly, potential difference equals current times resistance. An electric heater has a resistance of 1.2. It draws a current of 20. Calculate the potential difference. So that's just timesing these two together. That should be 24. As the answer to that question. That is all of that done. So question 8 is done. Is that all right? Question 8? Yeah, good. 9, 12, and 11. Okay. I mean, it reaches a point where you should really be able to do these on your own, but I will continue. Let me see what else anybody has asked. The topic is physics. Um, the topic is physics, but physics involves a lot of maths. Um, you can't tell the answer on C. I don't know which one which C you're on about, so just tell me again. Question 3, question 3 someone has mentioned. Hmm. I'm not going to do that. I'll tell you what, I'm going to do the later questions because given that I've done 4 or 5 of these questions now, and I've shown you that if you just get the equation from the first page, the rest of it becomes a little bit easier. Oh, no, that's not true. I'll do it because this is a little bit of a harder question. Write down the equation that links gravitational potential energy, gravitational field strength, mass, and height. Now, the formula sheet will tell you gravitational potential energy equals mass times gravitational field strength times height. That's what it will tell you. Okay. It says calculate the energy of a 12 kilogram box, that is a mass, that's how heavy something is, at a height of 2.5 meters. So height is 2.5. And it tells you in the question to use this number for gravitational field strength. That is a fixed number that you will always get given in the question. It's always 9.8 on Earth. And so if you times those 3 numbers together, you should have your answer, which I won't work out for you. You should be able to do that. Similar question. Gravitational potential energy equals mass times gravitational field strength times height. The 12 kg box is lifted further. So 12 kg box. It now has this much gravitational energy. So 882 gravitational energy. Calculate the new height of the box above the floor using this number again. So that is 9.8, and the h is what we're trying to work out in this question. So it's a little bit more complicated, this one. What I'm going to do is whenever you get like lots of things being multiplied together in a question, just multiply them together. So 12 times 9.8, because it makes it all look smaller, is 117.6. It's being times by this letter h, so I'm just going to stick it on because that's what we do with letters and numbers. Now to work out what the h is, I will divide 882 by 117.6, which is 7.5 as the answer to that question. Right, what was someone asking? Question 2C. Oh, I'm not done 2C yet. 2C. Right, I don't know what anybody's saying here at the moment. Okay. 2C, year 9. Okay, right, I'll do 2C directly. So there is a formula on your formula sheet that says kinetic energy equals 0.5 times mass times velocity squared. That's important. The question in part C says a car of mass 450 kilograms, so the mass is 450, gains this much kinetic energy, so the kinetic energy is 3,600. The 0.5 is a fixed number. Calculate by how much the velocity increases. So we're going to work out what this v is in this question. What I need to do first, as I said, if you've got lots of things being multiplied, just multiply them together. 0.5 times 450 is 225. Okay, now I'll continue working straight down. I need to divide this over. So you divide that over. And you will get 16. Now, this question is not finished because of this v squared. When you have v squared equals a number, when you want just v, you square root the number on the other side, which is a little bit more complicated. But you will get there. That's 2c done. Right. I mean, I've pretty much done every question here, haven't I? 9, 12, and 11. Okay. Write down the equation that links potential difference, current, and power. So you're looking for an equation that says potential difference, current, and power. And look, I found it. Power equals potential difference times current. Okay, so written that down. Calculate the power of a motor that operates with a potential difference of 30, so that's 30, and draws a current of 5. 30 times 5 is 150. Done. This one's a little bit more complicated. Power equals potential difference times current. Right. The reason this is more complicated is because of these units here. These kilowatts have to be turned into watts by timesing by 1,000. So it's 2,500 watts first. That is the power I'm going to put here. That is a potential difference. As I said earlier, potential difference is another word for voltage. It's measured in volts. So whilst these questions don't explicitly say this is the potential difference, when you see the units V, it can tell you that that's what it is. So 230 times current. If I want to work out current now, I divide 2,500 by 230, and I will get 10.9. Okay. And power equals potential difference times current. In the USA, a 1,500 watt. This, again, this is why it's important to know the units. It doesn't say the power is 1,500, but because it said the unit watts, you know, or I know, that is a power. Current 12.5. And so if I want to work out the potential difference, I divide 1,500 by 12.5. And I get 120 as the answer. Let me see what anybody else has said so far. Okay. Um, I really shouldn't have to do. I'm just deciding whether I should do these questions because I'm just slightly concerned that you're asking me these questions because you just haven't done them yet and you feel like I should just do them for you because some of them are not difficult. This is not any more complicated than any of the others, so therefore no. I'm going to decline question 10. I think 11 somebody asked as well. 5, A, B, and C I've already done. But remember, this is recorded, so you are able to access the recording later. 12 has been asked, and I think somebody said 11 as well. It literally is the whole thing. 9, 12, 11, yeah. Yeah, I don't see any reason to do this. Because if you just get this equation out, you should be able to put the numbers into the right place and do everything I've done so far today. Question 12 I'll do just because the equation's a little bit different. The formula will say density equals mass divided by volume. Somewhere it will say that, I promise. And also this is a little bit harder, actually. This is much harder, this question. So this is a fair way to finish this part. Calculate the density of a box of mass 200 kg. So the M is 200 and the volume is 0.85. 200 divided by 0.85 will give you your density. Again, At this point, don't worry about fully understanding what these different things are. Like I wouldn't expect everybody, certainly in year seven and stuff, to understand what resistance is or potential difference or density necessarily, but you will get there. At the moment, it is just showing you that these questions are not that difficult to get right as long as your maths is sufficiently good. Um, right, the question is, well, the formula is density equals mass divided by volume. Okay, this is a bit of more maths involved here. So more questions are coming. What if you're bad at maths, though? Well, that's why we're here, to help improve everything at once. So, density is 1.2. The mass is what we're working out. Now, this question does not directly say what volume is. However, let me explain what's happening in this question. Because it gives you this, and it doesn't say the volume is this. It says it's a room that measures this much. That's not the same as volume. So what's happening here is that imagine this is your room. Okay, that's a room, 3D. It measures 3 meters one way, 4 meters the other way, and 2.5 meters the other way. Now, from those measurements, again, if your maths is all right, you would be able to tell me what the volume of that room is. Because to find the volume of it's a cuboid. I've made it like a cube, but it's a cuboid because of the measurements. You multiply the three lengths together. So if you do 3 times 4 times 2.5, you will get 30. 30 is the volume of this room. So the 30 is what goes into the equation over here. And then to work out the mass, you multiply 30 by 1.2 and you will get 36. I would argue that that is the hardest question on here so far, just purely because it requires an completely extra step to work out the volume. Gold has a density of 19. Oh, this is also, I would say, I'd argue this last question is wonderfully slightly harder. Density is mass divided by volume is the equation. The density it tells you is 19. Oh, right. And then it wants the volume of 1 kilogram of gold. That is a mass, just to be clear. Kilograms are units of mass. However, the reason this is a slightly more complicated question it's good to do these slightly more advanced things, is because the unit for density here mentions grams and the unit for mass is in kilograms, we cannot just put the number one into here where the mass is. We need to make sure the units are consistent. So if the grams here, then we need to make this grams as well. That is 1,000 grams. That 1,000 is what will go here for the mass. And then if you want to work out volume from here now, volume is going to be 1,000 divided by 19. I'm skipping a step here just to speed things up a little bit. But that is the calculation from here to work out what the V is. It's 1,000 divided by 19, which is 52.6. Right. I wasn't expecting quite so many questions and doing the whole thing. Do we write out the notes for this week? Always, yeah. 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 It depends. You should have been told in your lesson specifically what you have to do um, with regards to the notes. And I don't know who's asking the question because you're anonymous and therefore I cannot really be specific with you. The last thing I will say is, do we need to put the units? No, I mean, in general, I think I mentioned this earlier, you might have joined a little bit later, but in general, when you do these questions in an exam, there are two possibilities. So they ask you the question, and then at the end of it, they leave a line to write your answer. Now, often you will find that they will write the units of the answer already here, so you don't need to worry about it. You just write the answer in the space, and that's it, done. Sometimes they won't give you the unit, and the question will say, state the unit in your answer. Now, for these specific questions, because we were focusing mostly on just how you rearrange equations, we're not worried about the units for this specific homework. Okay, we just want you to practice putting the numbers in the right place, using the equations, and so on. Also, just lastly, before I finish this bit, the person who is here who was asking me about the chemistry from last week, we will talk about that on Sunday. Because you have a test on Sunday, there'll be plenty of time to do that, because I just didn't expect quite so many questions and ended up doing the whole booklet um, today. So, yes, we will make sure. So don't worry about it. Anything you don't understand, we'll just talk about it at the beginning of Sunday's lesson. Um, the one thing I will just say lastly to finish for all of you people, because you are all in years 7, 8, or 9, you are in the exceptional situation currently as it stands for GCSE physics when you get there, which is that right now, the physics equation sheet that people in year 10 and year 11 get looks like everything you can see on your screen right now. In other words, it's quite big. Okay, they get every single equation that they could possibly need to answer any physics question given to them at the beginning of the exam. They don't need to learn any of the equations. However, if you are in year 9 or below, which all of you technically are, unless you are here a bit early, you will get an equation sheet that looks about this much size-wise. You will have to learn about this many equations for your exams, as in memorize them, just because. Okay, so that's the situation, just so you know. A lot of these equations that you're doing in these homeworks and stuff, eventually, not now, you will need to have actually learnt them. You won't get them given to you like this. You'll get about half of these equations that you can see here in your exam, and the other half you will have had to have learnt. The tests are all for all of you in your next lesson, actually. So if you're attend on a Thursday, it's tomorrow. If you attend on a Friday, it's on Friday. If you attend on Saturday, it's on Saturday, and so on. Yes, it is in your next lesson. Okay. Don't worry too much about the test. I always say this. I have sent an email. It has all of these resources like notes and videos and stuff if you want to go through them. Um, the point is, it is important for you to do tests to practice doing tests, which just sounds like a strange thing to say, but it is important that you just get experience of doing tests, no matter how you do in that test. To me, it's not that big a deal at this stage anyway. It is just practice that these are the style of questions that you're going to get. You get some experience of doing a test, and that will make you better at tests overall. All of the topics on the test are essentially these, which are the topics you did in the first 4 lessons. Now, I appreciate that some of you joined a little bit later and therefore missed some of these lessons, but that's why I sent an email which has lots of notes and resources. They are the topics we did in the first 4 lessons of the year. From September, we did cells, we did atomic structure and chemistry, we did energy and physics, we did rearranging equations in maths. You get all of them together in one like test. It has a biology section, chemistry, physics, math. It's all one document. Got an example of it there. And you also get a little verbal test as well, where your tutor will spend 5 minutes with you asking you some questions verbally, like, for example, do you know the differences between a plant cell and an animal cell? Or do you know the charge of a proton? Things like that. Okay, you'll be asked that verbally. Yes, if you've been for 1 lesson, you will be doing the test. Everybody will be doing the test, even if it's their very first lesson. So you're at an advantage. But yes, that is the reason why you were sent some notes and you have access to everything. As I say, it's not about how you do in the test. You just need experience of doing these things. It is important. So don't worry about it too much. We are aware that you may have only have had 1 lesson here and so on. But you do the test regardless, because we can't do the test with everybody else and not with one person, because that would not make sense. What about the maths? I don't know what your question is. What about the maths? Rearranging equations is a maths topic. Answer your question. I don't know. Okay, right. Assuming there's no more questions, what I'll do is I'll go get a coffee and I will be back here at 8 o'clock to do anything that year 10 and year 11 want me to do. So, all the best with your exam. I'll see you at the weekend if I'm teaching you. If not, yeah, I'll be back soon. Hello. Um, right, let me answer one of these questions. You know when magnetic materials only attract? If I flip the magnet's pole next to it, will the materials well? It's a slightly unusual question that. So a magnetic material is not a magnet, which means it doesn't have a north and a south pole. Magnetic material is like something like iron or copper, that just not copper's a bad example, iron or steel, I think, that is attracted by a magnet. So you flipping the magnetic pole next to it in that situation would make no difference. It would still attract. It's only when two magnets are near each other, then the north and the south pole makes a difference. But magnetic material doesn't have a pole as such. So yeah, right. The usual suspects have asked lots of questions. Um, Questions 3B, 3C. Okay, right. Let me decide once again the likelihood of me answering all of these questions for you. Um, I've got a feeling some of this was a challenging booklet. Um, right. Question 3B. I mean, okay, I'll answer it, but I shouldn't. Um, this is showing you. Oh, I'll zoom in. 1 minute. Oh, year 11 booklet. Sorry, I always forget. I'm just thinking of last year. 3B, 3C, right, again, right. Year 11 did electromagnetism. It's fitting. Let's see if anybody else got any more questions on this. Um, I've been asked to do quite a lot of questions from this booklet, so chances are. Um, which booklet are you asked? 6A Part 2. Which booklet is that from? Is that the electromagnetism one? Mm. Yeah, 10. Okay, right. That's all. Just specify when you do it. Um, okay, I will go to that first. It's the only one I've got from that, so I will do that first. 6A Part 2. Let's see what's going on here. This one. Um, right. In the UK, over 70% of the electricity is generated in power stations that burn fossil fuels. Explain one effect that burning fossil fuels has on the environment. Okay. Give one way the effect on the environment could be reduced. Assume the amount of fossil fuels burnt stays the same. Um, okay. Think about that. So if we're still burning the same amount of fossil fuels, how could we reduce the effect on the environment? Um, Oh God, that's a tricky question. Well, what we could do, I think the easiest answer to that question is at the same time as doing all this, you could plant more trees. That would probably be the easiest answer. There's a few different answers, but I think the easiest answer would be that you plant more trees. That way, the effect on the environment will be reduced, right? Because when you burn fossil fuels, what happens? We release carbon dioxide. But if we could plant some trees at the same time, what will the trees do? They will take in carbon dioxide via a process called photosynthesis. So that would reduce the effect on the environment. I would say that's the easiest answer out of all of the ones available for that question. Right. Again, if you're going to ask a question, you need to tell me what year booklet you're asking me for. If that's all right, but I think that's the year 10 one, isn't it? Question 7, part 2. What does a step-up transformer do? Yep, some of these questions are a little bit challenging, but one thing I would advise you guys to do is I appreciate you can definitely come here and ask me. That's not a problem. But also, what could save you time for a question like that is you could pretty much just Google it and you would get the answer. Um, so, what a step-up transformer does, let me just briefly explain what happens here, is that when we get electricity out of a power station, before we send it down all these big cables, what we do with a step up transformer is increase the voltage to a very high level. Now, this wouldn't have been covered in the lesson, just so you'd be clear. It's because it links to electricity and it's very hard to avoid all of the questions. But it increases the voltage. But what that does, the reason we increase the voltage, step up the voltage, is because we're trying to decrease the current. If you increase the voltage, you decrease the current. If the power stays the same. And what that decreased current does is it prevents the wires from getting too hot. So the best answer is to reduce the current. in answer to that question. What step-up transformer does. Um, how does the material stay the same? Um, I don't know what that means, that question. Um, because I'm explaining. Oh, sorry, this was going back to my previous explanation about magnets. I'll come back to that. What sort of question would you get asked in the exam about this topic? Well, technically, once again, let me just remind you all what topics are in your should be in your exam. So energy. Now, technically, we did energy twice. We did something called Energy A with year 10, where we did more about the equations like gravitational energy, kinetic energy. You're probably likely to get some of those equation questions. I think you'll get given the equations, so you don't have to learn the equations, but you need to be able to use them. Um, the topic that you did last time, this topic that we're talking about, shouldn't be on it, but you should have some awareness of burning fossil fuels and so on, which I think everybody does generally. That is the that's the physics topic. The chemistry topic for year 10 will be atomic structure and periodic table. Um, you did bonding a couple of lessons ago. There should not be too much on bonding, if anything. You know, because it'll be should be on the next test you do. This is mainly the stuff that you've done in the first 4 weeks here. So energy, in physics, atomic structure in chemistry, cells in biology, and then the rearranging equations in maths. Just for those of you in year 11, very quickly, let me tell you, you did some stuff about on homeostasis. I would focus your attention on the stuff to do with controlling blood sugar levels because that's the bit that you did then, controlling blood glucose and insulin, glucagon, that sort of stuff. In biology, in chemistry, you did organic chemistry, alkanes and alkenes and stuff. In physics, you did radioactivity in September, alpha, beta, gamma radiation, that stuff. In maths, you did vectors. I warn you that this is not easy when a whole maths topic test is basically on vectors. I think there's the odd one or two rearranging equations in there that you should be fine with, but that is what that is. Right, let me go back to some of these questions on here. Now that I've done that. Question 3A has been asked. Okay, I shouldn't need to answer question 3A. But use words from the box to match the correct energy source to each of the descriptions given in the table. So the description is energy from the Earth's core. The Earth's core is like in the middle of the Earth where we've got lots of heat energy. If we use that energy, we call it geothermal energy. Fission of uranium nuclei. This uranium is a radioactive nuclear substance. So that's what we do when we're using nuclear energy. And the gases from rotting plant material are burned to heat water. When we grow plants and then burn them, um, it is called biofuel. That's what that is referring to. Um, did I do seven part two? Yes. And done 3A, year 10, 6. See, I knew what this question was. So question six, oh, seven, sorry, 6C part two, this one. So there's some information here about electricity. Um, okay, between 2000 and 2000, the amount of electricity used for lighting in homes in the UK decreased. The amount of electricity used for lighting in homes decreased. Like, I'll check the answer for this. My instinct says it might be something to do with bulbs. Yes. We started getting more energy efficient lighting, like those like halogen bulbs and things. So saying that we developed energy efficient lighting would be fine. You could also just say that people were um, becoming more aware of the environment, and so they turned off the lights and stuff when they didn't need to use them rather than just keep them on all the time. Okay. Sorry, I'm just getting through any of the year terms. Would we get asked maths questions in the verbal test? No, there are no maths questions in the verbal test. The verbal test is purely biology, chemistry, and physics. Hmm. Right. I think that is covers what the question the people in year 10 have been asking me. So yeah, 10, 6, 7. Yeah, I think I should move on. Well, if you have any other questions, I can click back over if necessary. Right. Electromagnetism in year 11. I will say one more thing about electromagnetism for those of you that are here. Um, year 10, 7A part. Didn't I just do that? I did do that just now, didn't I? Oh no, 7A part 2. Okay, well, I'll just quickly explain this, which is what they do is they prevent, because we reduce the current, they prevent the wires from getting too hot. So less energy is wasted. If wires get hot, it is a waste of energy. And so we basically preserve that by doing that. Um, page 10, question C, part 1. Let me just check. Oh, read the extract below. In the future, it may not be possible to have constant electricity. Families have to get used to using power when it's available. In the UK, the proportion of energy in wind turbines is due to increase a lot. Some opponents of wind turbines will cause big fluctuations. One reason why this may be true. Well, if you were relying on wind energy, let's say you had to charge your phone and you were only could charge it if we had wind energy. Well, then you wouldn't be able to when it wasn't windy, would you? And so there will be big fluctuation in electricity supply because essentially it's not always windy or wind energy is unreliable. Um, that would be fine. Wind is an unreliable energy source, right? It's not always windy. So yeah, 10, question 8. Let me have a look at what that says. This one. Ugh, okay. I might just talk through this briefly. This shows all the energy sources used in Canada in 2014 and a prediction for 2040. Okay, 2014. Okay, we've got some stuff here in 2040. Discuss the effects of the amount of two predicted changes. Right. So let's pick on it's so hard to see these colors. Right. Let's pick this one here. It depends on what you pick, really, so I can't really answer this question entirely. But if you pick this one, let's say the natural gas with this like hashed thing, um, then we are increasing by 2040 the amount of energy we're getting from natural gas. Natural gas is a fossil fuel. So what you want to do is the change is an increase in natural gas. The effect on the environment is it would um, result in more carbon emissions because when you burn any fossil fuel, you get more carbon emissions, or you can say more greenhouse effect, more global warming, that kind of thing. You could then pick on wind energy, which has gone from 7% to 11%. That has the opposite effect. So you can say wind energy is increased. What does that do to the environment? It results in less carbon dioxide emissions because wind is a renewable energy source, that kind of thing. Or you could say that if we increase wind energy, it would look bad because more wind turbines will be around and so on. So you need to pick them and then say the effect on the environment for those. Um, the future demand for fossil fuels is expected to increase. Give two reasons why scientists are worried about the increase in demand. Well, my immediate answer to this question, without really looking at the answer, is that if there is a more demand for fossil fuels, that means more people want fossil fuels. Why is that something to worry about? Well, fossil fuels are non-renewable, which means that they can't be reused and they will eventually run out because it's non-renewable. So that's the first worry. The second worry is that if we keep on using fossil fuels, we will increase the greenhouse effect and global warming, which will result in more ice caps melting and sea levels rising and that kind of thing. And then why does the government want more nuclear power stations? Nuclear energy is very reliable and gives us a lot of energy. And also, it doesn't emit greenhouse gases when we burn, well, when we use nuclear energy. So that's why the government might want more nuclear power stations. Essentially, the question is, and there should have been in your notes, the advantages of nuclear energy. We produce loads and loads of energy from nuclear, and it doesn't emit any harmful gases. It has its disadvantages, but this question is about its advantages. Um, and yeah, I can do that yourself. Question D3. Yes. Right, I think that's done. I'm done with those ones. Right, I'm going to move on. So, I don't know why we put the equation sheet in here. Right, let me go to the year 11 booklet. That's done with the year 10 stuff. Um, Right, electromagnetism is the topic. I will just do the questions in order that have been asked. And if you want to have any other questions about this topic, then feel free to ask me. Oh, yeah, I was going to say, which is that we do or did the topic of electromagnetism this week. We actually do it again in a couple of months' time, partly because it's unlikely we got through absolutely everything you need to know, especially if you're doing triple science. There's more to know. And so we do it again because it's quite a complicated topic. So we do it twice this year. Um, 3B has been asked. Where it starts. Right. Good question, this. And this kind of answer, oh, no, it doesn't. Never mind. One block is a permanent magnet. One is iron and one is aluminium. Right. This requires a little bit of knowledge. Aluminium is not magnetic. Okay. Firstly, I just want to point that out. Iron is magnetic. This is a magnetic material. Okay. And a permanent magnet, what you need to understand is a permanent magnet has a north and a south pole. That is important. Okay. Um, How could another permanent magnet be used to identify what is going on here? Another permanent magnet to identify which one's which, just to be clear. Another, make me read the question. Okay, so let's say I had another magnet here, a north pole and a south pole. How could I use that to figure out which of these is the magnet, which of these is iron, and which of these is aluminium? How could I do that is the question. A very common question here to really test your understanding of the difference between permanent magnets and magnetic materials. This is so important. Okay. A magnetic material is something that is always attracted by another magnet. It's important. Okay. But what we need to do is to identify these blocks. What we need to do first is we need to put the magnet or the magnet that we've got near each of these blocks. Now, when you put it near aluminium, what will happen? Given that I've told you that aluminium is not magnetic, nothing will happen, no effect. So whichever one of these three has no effect is aluminium, right? If there's nothing, no attraction, nothing, it has to be aluminium. Okay. Right. How do we then figure out which is the magnet and which is the iron out of these three? Well, iron will always be attracted to the magnet. No matter what you do, it will be attracted to the magnet. Okay. No matter which side of the magnet you use, whether it's the North Pole or the South Pole, it will always be attracted to it. Now, the permanent magnet, though, will be attracted to one of the poles. So let's say this is the magnet, and I put this North Pole near here. No, this near here. What will happen if I put the North and the South near each other? It will be attracted to one of the poles. But if I put it near the other end of it, what will happen to it? It will be repelled by the other. That's how you know which one is the magnet and which one isn't the magnet, because this piece of iron, which is a magnetic material, will never be repelled by another magnet. It will always stick to it. Whereas two magnets, depending on which side you put them, will have some repelling going on. That's how you can tell the difference. It is a very common question, this, to test whether you understand that a magnetic material will only attract to a magnet, whereas two magnets can repel depending on which way around you orient them. Right, that covers that one. Um, what other question do we have? 3B, 3C. Um, right. This shows a toy crane and it uses an electromagnet. So really this question is, do you understand what is an electromagnet? How can this electromagnet pick up and move the blocks? So what you need to explain here is that you were 6 marks, is that when you press the switch, okay, press switch, I'm abbreviating this answer, what will happen? You will complete a circuit, okay? That's what a switch does, right? Remember from electricity? Circuit completes, a switch completes a circuit. And when you complete the circuit, current will flow through the wires. Okay, so now what we've got is current flowing through, do this in green, this wire. Okay, right, current flowing through. Now, when a current flows through a wire, it has a magnetic field around the wire. Okay, or it creates a magnetic field around the wire. So now there is a magnetic field around the wire, and because this wire is coiled up here, as you can see that increases the strength of the magnetic field. And when you put it around you probably don't need all this information, but I'm going into more detail than necessary. When you put the wire around a piece of iron, which is what they've done here, it increases the magnetic field even more because the iron becomes magnetized as well. Okay, so the iron, which is what this is, it doesn't say it, but it is, um, becomes magnetized. And so now we have a very strong magnet here. In other words, an electromagnet. Let me just make sure I haven't missed any information for that question. What else could we have said here? Complete the circuit, turns the electromagnet on, current in the coil, magnetic field around it, iron core becomes magnetized. Right, fine, that's all correct. And then once this is now a strong magnet, when you move this close to the magnetic materials, what will happen? So you move the electromagnet towards the blocks, and the block will be attracted to the magnet, which allows you to move it around. And crucially, by turning the switch off, it turns off the circuit, turns off the magnet, and you can drop the magnetic materials. That's the whole point of an electromagnet, that it can be turned off. Is important. Um, I won't probably have time to do any space physics, but if you contact us, I can send you literally, it's a very small chapter of the textbook that you can just read through. Um, well, I might just show you. Well, I should have time. Let me see if I can, how long it takes to get through all these questions. Um, for, okay, I'm not answering question four. Absolutely no chance I'm answering question four. Um, question five. Yeah, it's a bit awkward, this one. Right. The diagram shows apparatus used to demonstrate the electric motor effect. When the switch is closed, the wire moves. So this is demonstrating the motor effect. The motor effect happens when a wire that's carrying current is in another magnetic field. So because of these magnets, right, there's a problem in this question. It doesn't tell you where the north and south pole is. Okay, we can assume that the North Pole is there and the South Pole is there. Draw an arrow on the diagram to show the direction the wire moves in this question. Well, you got to get, it's very hard for me to show you this. But firstly, what you need to do in these questions is identify the direction the current is flowing in. Look for the big line on the battery. It's starting there, and then it's going to go all the way around. And so it's going to be going in that direction, okay? And then it'll complete around here. So using my left-hand rule thing, okay, I think there's a problem in this question. Yeah, no, there isn't. So, well, there is. They should really label the North and South Pole, but you can assume that that's the way around it is. So I can't, it's impossible for me to show you this. But if you got your Fleming's left-hand rule out, yeah, that thing, right? You're meant to point your first finger sort of downwards, because that's where the north to south direction is. The second finger goes in the direction of the arrow that I have drawn, which is where the current is flowing, and your thumb ends up pointing in that direction, which means that this will move in that direction. And the reason the wire moves is because, this should be 2 marks, it is, because there is a magnetic field around the wire, as we explained with the electromagnet earlier. And there is a magnetic field um, between the North and the South Pole. And the crucial word that you have to use here, remember this when you do your exams, you need to explain that these two magnetic fields interact. Sadly, you have to use that word. Okay. Um, right. 3, 4, 5, 6, B, C, and D. Um, okay. Slightly harder question, this one. Um, So, a student investigated how the number of turns on the coil of wire affects the maximum voltmeter reading. The student changed the number of turns on the coil on the wire, then moved the magnet into the coil. The student recorded the maximum. To obtain valid data, two variables students control in this investigation. Probably the type of wire. Let me see what the answer says. Um, so you need to use, if you're going to do this experiment, then you should use the same strength magnet. This is quite a difficult topic. This goes into the next time we do um, this topic. But for your knowledge, things that you should control are things that that should stay the same each time you do this experiment. So what you're doing is you're moving this magnet through this coil of wire, and what you're doing each time you do this is adding more coils. So you need to make sure you use the same type of magnet or same strength of magnet. And the other thing, which you wouldn't know necessarily, is that you should keep the speed of the magnet the same when you're moving it, because the faster you move it, the more voltage you're going to get. Okay. I forgot what this last year 10 questions have been answered, but you can ask me, and if I haven't answered one of them, then I can tell you. Otherwise, you can watch the recording back of it. Um, I'm not doing that. Draw a line of best fit and all that stuff. A data logger, just so you know, is something that basically is something that's connected to a computer. Um, and so rather than you manually checking data when you're doing an experiment, the computer will do it by itself, which means it can take much more readings. It can do it much faster, basically. So you want to be able to say that a data logger can take more readings in the same amount of time, um, essentially. So that's kind of it. 'Cause it's just a computer doing it all for you. Um, okay, I have been asked 7B, 7C, and loads of question. Okay. Um, okay, the reason I'm not answering these questions is because it's essentially always the same with this topic. With this topic, if you need a bigger force or a bigger spinning, because that's what this is all about, the motor effect leads to this spinning motion. The answer is kind of always the same, which is if you increase the current that's going through the wires, you get a bigger force on the wires. Or in this case, making it spin faster. If you use stronger magnets or increase the strength of the magnets, the same thing happens. You get a bigger force or a faster spinning. So it's always the same answer, which is why I don't do that. Similarly, these questions are always the same as well. That if you have this spinning motion, due to this motor effect. If you want it to go in the opposite direction, you can either reverse the current, so it goes the opposite way round. So rather than it going this way round, it goes the other way around because that swaps the direction of the force from Fleming's left-hand rule. Or you could change the pole on the magnet, swap the poles of the magnets. Again, that causes the force to go in the opposite direction. These questions are always um, basically the same thing. Right, and you've asked for 8C, 8CHT. Um, well, once again, I'm not answering that because it's essentially the same question again. Um, and this is important, that this situation here, as you can see, this motor effect that you learnt about, which is when a wire carrying a current, which has a magnetic field around it, is in another magnetic field, it experiences a force. It moves by itself, and that's what leads to the spinning of a motor. It is important, if you want to maximize this effect, that this wire is perpendicular, in other words, at right angles to, or at 90 degrees to, the magnetic field. Only then will you get the biggest force. If it's like at an angle, Rather than being straight down, it's like at an angle. It won't experience as big a force. And so when it says here in this question, what is the position of the wire, it needs to be at 90 degrees to the direction of the magnetic field. Um, and then you mentioned question one, which is this one. This is the same question as before. Um, okay, so you've probably seen this experiment before where you're like picking up paper clips with a magnet. Um, So we're investigating how the number of turns on a wire. Remember, an electromagnet is like a coil of wire. The more coils you have, the stronger the magnet will be. So what we're trying to do is figure out, actually see that happen. So we're going to change the number of turns, see if the magnetic field gets bigger by picking up paper clips. So if it's a stronger, if we've got more coils, we should pick up more paper clips, right? Two variables that you control, things that should stay the same. The weight of the paper clips should stay the same because if you're using some heavy, some light, it's not going to be fair. So the same type, size, mass of paper clips. And also, how do we get this magnetic field anyway? It happens due to the current in the wire. And so if we're going to investigate just the number of turns, we should keep the current the same because otherwise a bigger current would actually make this magnetic field stronger as well. So you're controlling the current and also the size of the paper clips. And there's probably more answers. There are some results. You can do that yourself. Um, okay, right. I think that covers all of those, doesn't it? Right. Let me just revert back to this and see if I've answered any other questions. Somebody said question 8. Okay, I did explain question 8. Essentially, for question 8, very quickly, what you need to do is compare pick any of these, pick any of the colors, and just state what happened. So if I pick wind energy, say wind energy use has increased, right, between 2040 and 2040. But what effect does that have on the environment? Well, if you're using more wind energy, you're going to get less carbon dioxide emissions because wind energy is renewable. Alternatively, you could look at natural gas. That has increased. And then the effect on the environment is that that would increase carbon dioxide emissions or increase global warming because it's a fossil fuel which we burn. So it's really testing you on that stuff. And then let me just check. Question 7, part 3. I did answer that. And basically, and you wouldn't know this yet, but you will do it when we do electricity, which is that step-up transformers, what they do is they reduce the current going through some wires here. Reducing the current going through a wire um, basically prevents them from getting hot. And if they don't get hot, we waste less energy. 6 part 2, I'm pretty sure I did as well. Yeah, this was why would we have suddenly used less electricity for lighting in those 6-year period? It was to do with the energy efficient lighting. Like we've developed bulbs that don't use as much electricity and so on. And so they would do that. Or you could just say that we were more aware of the environment and we might be turning lights off more, that kind of thing. And D on the last page. Oof. Wow, there's lots going on here. How much did the total world's energy use increase from the year 1971 to 2003? I think that because this is like layered, what you can do is just go to there. That's how much energy we were using or we were using in 1971, which looks like 5.5 to me, roughly. And then by the end, 2003, we were at 10.5. So it's increased by 5. That seems to be the answer to me. Which energy source had the greatest use in 2003? It would be the section that is the widest. So that to me looks like the wider section, which is oil. And the total energy use in 2000 was 10.6 billion tons. What percentage of this amount was due to fossil fuels? Oh, God, that's a tricky question. Fossil fuels are these three, right? Remember, there's three fossil fuels, and I just warn you, when you do your verbal test, there is a high chance you get asked about what the three fossil fuels are. Coal, oil, and gas. So that means that that's coal, that's oil, that's gas. So in total, That is about 8.5, and I'll call it 8.5. It's an approximating question. So out of the 10.6, 8.5 came from fossil fuels. So if you do 8.5 divided by 10.6 and turn it into a percentage by timesing by 100, you'll get about 80%. And I think that should be close enough to the answer. Um, and that is everything. Um, the topics on the test this week, just to be clear, not next week, this week, at the weekend, for year 11 are homeostasis, mainly because homeostasis is a huge topic. Homeostasis includes the nervous system, which you technically did with us last year, um, the stuff about controlling blood glucose, insulin, glucagon, and it includes stuff to do with the menstrual cycle hormones, FSH, LH, and stuff, the I would be prepared more for the sugar bit. So insulin and glucagon and diabetes, that part. Organic chemistry, alkanes and alkenes, fractional distillation of crude oil. Radioactivity is alpha, beta, gamma radiation. Half-life, that kind of stuff, and vectors and maths is what you did. So it's basically what we did in the first month here. For year 10, it is energy, atomic structure, cells, and rearranging equations in maths. There seems to be one more question that's come in. 6A part 2. This will be the last one I do because I need to do something else. 6A part 2. I mentioned planting more trees for that. So if you are still burning fossil fuels, one way you could help the environment is planting more trees at the same time, because at least they will take in the CO2, whereas the CO2 will be released by the burning of the fossil fuels. Right, last thing I'm going to do, given that somebody asked, I'm just going to show you the section of the textbook that talks about space. This is only in triple science, if you are doing triple science. We don't specifically do a lesson on space, but you will have access to something that will help you deal with it. We will do it automatically near the end, but we don't have a specific space lesson because it's too short. I'm not doing radioactivity, no. Um, you have videos, you have everything. I've made a video on radioactivity, so all you need to do is watch it. You can basically the same thing as what you're doing now. Just have to press play and I'll start talking. Um, right, in space physics, quite a small topic, as you can see here. Um, the life cycle of stars, the solar system and orbits, and redshift and the Big Bang, which is a reasonably complicated theory, the redshift thing. But I will tell you, without going through it, what I would recommend, depending on how much you've done of this. The big part of the topic of space, at least the big question that you can get, is to do with the life cycle of stars, which more or less is summarized by this picture. A star is starts its life as what's called a nebula, which is a cloud of dust and gas, and then it becomes a protostar. It then becomes a main sequence star, which is when hydrogen and helium are reacting together in a process called nuclear fusion to give it all of the energy that it has, like our sun at the moment is doing that. It is a main sequence star. Um, at the end, then what happens eventually to all stars is they either go on this top path or they go on this bottom path, depending on how big they are. So big stars become what's called a red supergiant. They then become a supernova, and then they become either a neutron star or a black hole. Whereas stars that are smaller or about the same size as the sun or smaller, they become a red giant, then a white dwarf, then a black dwarf. Essentially, if you know this picture, you can't really go wrong with this topic because it just needs these words. Not a huge amount of detail. Um, yes, everybody has to do the test, irrespective of when you joined. You were sent a week ago, a week, you've had a whole week to watch all of the videos that I sent to you because you have access to them. I sent an email on exactly a week ago, actually, with the notes and the videos that relate to the test. So yes, everybody does the test, irrespective of when they joined. It's good practice, okay, just to be point, and like you have GCSE exams very soon. It is good to practice, irrespective of how prepared you are. It's just experience of doing these questions. That's why we do them. So even if somebody was joining on this weekend, they would do a test regardless. It's just life. It helps you find out what you know and what you don't know. That's it, right? So it's more for your benefit than anybody else's. There is a bit more on this topic, which is to do with orbits. I'm not going to do the orbits bit. Just quickly on redshift, I just need to explain redshift to people, um, in case you are interested. If you were standing here and an ambulance was going by, that's meant to be a siren. Okay. Then, next time this happens, and a police car, same thing. Um, Notice this next time it happens. The siren sounds a certain way when it is near you, but as it's traveling away from you, it sounds different. Even though the sound doesn't change, the sound is the same. Okay. Um, and that is an example of redshift. Let me explain. The reason you hear this is because sound waves are traveling to your ears. But anything that's moving away from you, the waves actually, their wavelength changes slightly. Um, so the wavelength actually, as it's traveling further away from you, the wavelength, rather than being like this, becomes like this. Okay? It shortens slightly. And so any object that's moving away from us, the waves coming from it are shifted slightly. They actually shorten. We call that redshift. Okay. So red because the red end of the wavelength spectrum is the shorter end and the purple end is the longer. Oh, the other way around. Sorry, they get bigger. Sorry, so they get slightly bigger. Um, so basically that happens. Okay, any object that's traveling away from you, the waves coming towards you shift slightly, and we noticed that as we were looking at stars and stuff in the sky, the same effect was happening, as in the light that was coming from there was slightly redder because the wavelength had shifted slightly, it had become slightly longer. So the waves had gone slightly longer, so it looked a bit red, which told us that these things are moving away from us, just like this ambulance is moving away from you, because it exhibits the same effect, which is that the waves that are coming to our ears or eyes in this case are slightly shifted, red shifted. That's the point. And so that told us that all of these things that we're looking at in the sky, stars, planets, whatever, are actually moving away from us, just like the ambulance is moving away from us. And what does that tell us? It tells us that at some point they must have been closer to us because now they're moving away from us. If they were closer to us at some point, that led to the theory of the Big Bang. The Big Bang being where everything was concentrated close in one little thing together, and then there was a bang, and everything exploded, and it is now moving away from where it started. That's what happens in an explosion, right? Things move away from the central impact. And so we concluded, or we have a theory, that there was a Big Bang, and as a result of that, everything in the universe is moving away from us, just like the ambulance. That is what redshift is telling you. That is a simplified explanation of it. That is what it is. Um, how long is the science test and maths test each? The entire test is the whole lesson. I think I put 1.5 hours on the front of it, but if you need a little bit longer than that, that is fine. It is all in one document, so you could do how it's split your time however you think is appropriate. That should be plenty of time to do it all. And you also have the verbal test, which is why it's 1.5 hours technically, because there's a bit of time to do the extra bits at the end. If you need a bit more time, it is fine. What if you don't do well? Will you have to reset the test next week? Possibly. That's the best answer. I mean, the simple answer is no, but you know, we can always arrange for you to have another go at it soon enough. The good thing about tests is that it's not a lesson, is it? So you can always just come in and stay behind after your lesson or come earlier and do it. Which is why if you're not here this weekend, you will just do it another time. Don't attend online this weekend because there will be no lesson online. Right, there seem to be no other questions. And as I expected, we are going to finish slightly earlier today, partly because the Key Stage 3 stuff didn't take as long. Right, I think that's it. If you have any other questions, ask me now. Otherwise, we'll end this. No, that's it. Right, okay. I'll go home. See you later.